Hi, my name is Max Cuzetels.
My name's Ana Garcia. And my name is Akita Tosh. And we're going to take you deeper into the exploration of telescopes. Let's go!
Let's go, guys! Let's go look at some cool telescopes.
Beyond the Lens, diving deeper into JWST and telescopes, a journey from telescope fundamentals to the marvels of the James Webb Space Telescope and beyond.
Introduction to telescopes. Telescopes extend your vision by collecting more light than your eyes can. More collected light reveals fainter and more distant objects. Telescopes allow you to measure motion, distance, and physical properties of objects in space. Telescope observations change astronomy from philosophy into measurement-based science. Now moving to the history of telescopes. In 1608, Hans Lippershey builds the first practical refracting telescope using glass lenses. The device magnifies distant objects, which sparks interest among scientists and inventors. European instrument makers rapidly improve lens quality and magnification. And these early telescopes shift astronomy towards direct observation of the sky. Then in 1610, Galilei improves the refracting telescope for astronomical use. He observes mountains and craters on the moon, showing it is not a perfect sphere. He discovers 4 moons orbiting Jupiter, proving not everything revolves around the sun, and these observations support a sun-centered model of the solar system. Then in 1668, Isaac Newton designs the first successful reflecting telescope using mirrors. Mirrors focus light without splitting it into colors, improving image clarity. This design allows telescopes to grow larger without losing sharpness. Reflecting telescopes become the foundation for most modern observatories. And explaining image clarity, early lens telescopes bent different colors of light unevenly. This caused colored edges and blurry details in images. Mirror-based telescopes avoid this problem by reflecting light evenly. This improvement made faint objects easier to study. Moving on to 1700s to 1800s. Larger mirrors led to more powerful ground-based telescopes, and William Herschel discovers infrared radiation while studying sunlight. And astronomers began studying objects beyond visible light. Telescopes reveal nebulae, star clusters, and distant galaxies. Then in the early 1900s, mountaintop observatories reduce atmospheric distortion, and the Hooker telescope helps show that galaxies exist beyond the Milky Way. And spectroscopy allows astronomers to measure temperature, motion, and composition. Finally, astronomy expands from mapping objects to understanding how they work. Finally, in 1990, the Hubble Space Telescope launches into orbit above Earth's atmosphere. It captures sharper images without atmospheric distortion, and the Hubble measures galaxy distances and the expansion of the universe. Space telescopes open new windows on the universe across many wavelengths. Moving on to how telescopes work. First, we have light collection. A telescope works like a light bucket. A larger opening collects more photons each second. More photons raise the signal above background noise, so faint objects show up instead of blending into darkness. Doubling the diameter gives 4 times the light, which is why big telescopes reach much deeper into space. Collected light is focused onto an eyepiece or a camera sensor so you can record and measure it, not just look at it. Then there's magnification. Magnification sets image scale, not image quality. It depends on telescope focal length divided by your eyepiece focal length. If you increase magnification without enough light, the image gets dimmer and harder to see. If you increase magnification when the atmosphere is blurry, you just enlarge a blurrier image. A good goal is sharp detail first, then increase magnification only until the image stops improving. Finally, we have resolution. Resolution is your ability to separate 2 close objects, like 2 nearby stars. Bigger diameters improve resolution because they reduce diffraction, which is the spreading of light at the edge of the telescope opening. And shorter wavelengths improve resolution, which is why visible light can show finer details than radio waves for the same diameter. And Earth's atmosphere often sets the real limit for ground telescopes. So observatories use high mountains, adaptive optics, or space telescopes are even better to get sharper images. There are 5 key components of telescopes. 1, the light collecting area. 2, the angular resolution. 3, the location. 4, the wavelength range. And 5, the detectors and instruments used.
Now we're going to talk about the different types of telescopes there are. First, we have the refracting telescope, which uses a front lens to bend light into focus and makes for simple and stable optical paths. Some of the good things about this telescope are that it includes sharp contrast and sealed tubes that allow for objects to become clean and aligned. But some of the main downsides of this type of telescope is color fringing, which is when lens focus on different colors at slightly different points, and it softens fine detail, making the image less clear. Refractors work well for bright targets like the moon and planets, and for smaller scopes used in education as well as amateur observing. Reflecting telescopes use curved mirrors to focus light, which avoids the color fringing problem found in refracting telescopes and other simple lenses. The mirrors are easier to build in larger sizes, so most professional research telescopes are reflectors. A common design for a reflecting telescope includes the Newtonian, which basically folds light into different ways to fit the same collecting area into a practical tube. Some of the downsides of this telescope is that it includes a central obstruction that often can lower contrast, and mirror coatings that need cleaning and occasional recoating, which mirror coating is basically when there's aluminum coatings of oxide, and this degrades over time, which need recoating every few years. The next telescope we have is the cadiotropic telescope, which basically combines mirrors and lenses for a compact, versatile design that corrects optical errors. So basically, the corrector lens folds into a long light path and fits into a short tube. Again, this allows for long focal length and compact portable setups, which helps for higher magnification viewing and astrophotography. Some of the examples include the Schmidt-Cassegrain, which is designed to reduce distortion and keep images sharp across the field. Some of the downsides of this telescope is that it includes a narrow field of view, which basically means that this can cause edges of the field to appear out of focus, especially in wide field photos, but modern designs like Raza do mitigate this. Also, the cool down time seems to be very long for this type of telescope, since the closed tube can trap warm air that blurs the image at first. And what this means is that it takes longer to reach a good temperature, and this affects the image quality. Now we have telescope differences, which we're gonna talk about: optical, radio, X-ray, infrared, and ground versus space telescopes. First, we have the optical telescope, which basically collects visible light, the same part that the spectrum in your eyes detect. It helps you study reflected sunlight from planets, moons, and starlight from distant stars and galaxies. Cameras and spectrographs can attach to optical telescopes to measure brightness and split light into colors, and this reveals the temperature, composition, and motion of distant objects. These instruments are not limited to optical telescopes. You can use spectroscopy for various wavelengths, including infrared, UV rays, and even X-rays with special detectors. Now we have the radio telescope, which basically collects long wavelengths and passes through dust that blocks visible light. They map cold gas molecules, including neutral hydrogen, which allows the telescope to trace the structure of the Milky Way and other galaxies. Many radio telescopes work as arrays, where multiple dishes act like one larger instrument to sharpen detail in images. Radio observations also reveal pulsars, jets from active galaxies, and cosmic microwave background, which is leftover radiation from the early universe. Again, this allows for us to understand the development of the universe better and how the universe came to be. Now we have X-ray telescopes, which is basically a telescope that uses Earth's atmosphere since Earth's atmosphere blocks X-rays, the X-ray telescopes must operate in space, so not on Earth or in Earth's atmosphere. X-rays come from extremely hot and energetic regions in space, not from cool stars like the sun. They track matter falling into black holes, exploding stars, neutron stars, hot gases, and galaxy clusters. X-rays are focused using shallow angle mirrors because X-rays pass through normal mirrors instead of reflecting straight back to us. Finally, we have infrared telescopes, which detect heat, like radiation, which is light with a longer wavelength than visible red light. Infrared sees dust way better than visible light, so it reveals stars forming clouds and the centers of galaxies. Many infrared detectors must be cooled so the telescope doesn't drown out the signal with its own heat. Infrared studies include young stars, cool objects like brown dwarfs, and exoplanet atmospheres through absorption features. The main differences with these type of telescopes is the wavelength and energy. Again, we have radio waves, which are radio telescopes, which have longest wavelengths and the lowest energy. They detect cold gas, magnetic fields, and jets from black holes. Optical telescopes, again, use visible light, which is what humans can see. It detects stars, galaxies, and planets and its visible features. Infrared telescopes use heat radiation, which are longer wavelengths than optical, and they collect hidden star formation, cool dust, exoplanet atmospheres, basically cool stars and dust-obscured regions. And then X-ray telescopes use very short wavelengths, and they have the highest energies, which they observe black holes, supernova, remnants, etc. They observe extremely hot gas, accreting black holes, neutron stars, and supernova remnants. Finally, when we're talking about ground versus space telescopes, ground telescopes can be very much larger and easier to repair, so again, they collect more amount of light. Earth's atmospheres blurs images and blocks some of the wavelengths, so sharpness and coverage often can be limited from the ground, whereas space telescopes avoid atmospheric blur and observe using UV light and X-ray light, which never reaches the ground. To basically gain the best image, the best approach is to use both, using ground telescopes for size and flexibility, and then space telescopes for clarity and access to blocked wavelengths. Now we are going to talk about the famous telescopes in history, which is basically key milestones in the development and impacts of significant telescopes. In 1609, Galileo created and used one of the first telescopes for astronomical observations, and it marks the beginning of a systematic telescopic study of the sky era, and we learn about the moon craters, Jupiter's moons, etc. In 1990, we have when the Hubble Space Telescope was created. This telescope marked the first major long-term observatory of space using UV and visible light. It was launched into low Earth orbit, and it provided sharp detailed images of deep space, transforming modern astronomy. Moving on to 1993, we have the Keck Observatory creation. Basically, it's a ground-based observatory with high segmented mirrors in Hawaii. This telescope greatly increased observational power and resolution from Earth. Jumping to 2009, we have the Kepler Space Telescope designed to detect exoplanets by measuring tiny dips in stars' brightness, and this dramatically expanded our knowledge of planetary systems beyond just our solar system itself. Jumping to most recently, 2019, we have the Event Horizon Telescope creation, which is a worldwide network of radio telescopes acting as one large Earth-sized telescope. This produced the first ever image of a black hole, which changed our view of extreme gravity. Now we're going to talk about the design goals of the JWST. First, we have its infrared coverage for deeper insights, and basically the JWST is optimized to observe primarily in the infrared wavelength. Infrared capability allows us to see extremely distant, faint, and cool objects that are typically hard or impossible to detect in just visible light. It can observe light from distant past, which allows us to look back in cosmic time, basically time travel. It helps us track formation of the stars and planetary systems as well, which allows us to gain insight again on the formation of our universe, formation of galaxies, formation of stars, etc. We also see detailed studies of exoplanet atmospheres around distant stars through the infrared coverage.
One big goal is studying the earliest galaxies. Webb can see extremely distant galaxies whose light has been traveling for billions of years. So, when we look at them, we're basically looking back in time, like seeing what the universe looked like not long ago after the Big Bang. And that helps astronomers piece together the timeline of how galaxies formed, grew, and started to develop structure. Another major focus is star formation. Webb looks at regions where new stars are being born, especially inside the nebulae. What's really important here is that Webb uses infrared, which can see through thick dust clouds that would block visible light, so it can actually reveal young stars that are basically hidden from regular telescopes. This gives us a clearer picture of the earliest stages of star and planetary system development, like how stars turn on, gather mass, and start shaping their surroundings. And then there's exoplanets. Webb can study exoplanet atmospheres by analyzing the light that passes through an atmosphere during a transit, or the light that's emitted from the planet itself. Scientists look for chemical signatures, things like water, vapor, carbon dioxide, and methane. This doesn't automatically mean life, but it helps us figure out what these worlds are like, whether any of them could potentially have Earth-like conditions, and just how diverse planetary atmospheres can be. Okay, so now that we've talked about what Webb's design goals are, let's move into the structure and hardware that makes all of this possible. Starting with the primary hardware, the main mirror. Webb's mirror is made of 18 hexagonal segments. They're made of beryllium and coated with a thin layer of gold. The hexagon shape isn't just for aesthetics, it's so the pieces can fit together into one giant mirror, kind of like a honeycomb. Altogether, it forms a 6.5 meter mirror, which is huge, and that matters because a larger mirror collects more faint light, and faint light is exactly what you need if you're trying to observe dim, distant galaxies. Also, beryllium stays stable at extremely low temperatures, which is key for Webb, and gold reflects infrared really well, so it's basically designed around Webb's job, seeing the infrared universe. Then there's the sun shield. Webb has this massive multi-layer sun shield that blocks heat and light from the sun and Earth. That's how its instruments stay extremely cold, because if the telescope is warm, it gives off its own infrared radiation, and that would interfere with the faint signals it's trying to detect. So the sun shield is basically what allows Webb to do its most important work. And finally, the orbit. Webb orbits around the L2 Lagrange point, which is about 1.5 million kilometers from the Earth. The reason L2 is so useful is because the Sun, Earth, and telescopes stay in stable alignment. That means the sun shield can continuously block light and heat, and Webb gets steady, unobstructed views of space without constantly moving in and out of Earth's shadow. Next, I'll quickly go over the instruments on JWST. We have the NIR CAM, the NIR SPEC, the MIRI, and the FGS or the NIRISS. They are all key instruments designed to capture a wide range of infrared wavelengths and advance our understanding of the universe. The NIR CAM is a near-infrared camera for imaging and identifying distant galaxies. The NIR SPEC is a near-infrared spectrograph for analyzing the spectra of celestial objects. The MIRI is a mid-infrared instrument for observing star formation and exoplanet atmospheres. Then lastly, the NIRISS or the FGS is a fine guidance sensor or a near-infrared imager and slitless spectrograph for precise pointing and unique spectroscopic observations. Next, this part is about what JWST is teaching us about the early universe. Basically, what galaxies look like when everything was still really young. First, Webb's insights into early galaxies. Webb has already been spotting galaxies at extremely high redshift, meaning we're seeing them from very far away, and therefore very far back in time. Some of these galaxies are showing up just a few 100 million years after the Big Bang, which is crazy because it gives us direct clues about what conditions were like when the first stars and galaxies were still coming together. Now, to understand why Webb is so good at this, we have to talk about redshift. As the universe expands, light traveling across space gets stretched, so light that originally started out more visible can get shifted into the infrared by the time it reaches us. That's why JWST being an infrared telescope is such a big deal. It's literally built to catch the kind of light that early galaxies send us. And because it's so sensitive in infrared, JWST can see galaxies that are either too faint, too distant, or too redshifted for optical telescopes like Hubble to really capture clearly. So moving from early galaxies to something closer, but still super important, star formation. The Carina and Orion nebulae are basically classic star birth regions. They're filled with gas and dust, and you see these dramatic structures like pillars, jets, and these really complex shapes that are being carved out by young, energetic stars. The key advantage here is again infrared. A lot of baby stars are hidden behind thick dust, so in normal visible light images, you just can't see them. But JWST can look through that dust and uncover stars that would normally be invisible. So instead of only seeing the outside of a nebula, Webb helps astronomers study what's happening inside, how clouds of gas and dust collapse, how stars begin forming, and how young stars start shaping their environment almost immediately. Now let's talk about black holes in SEG 1. So start off, a dwarf galaxy is basically a small galaxy. It can still have up to a few billion stars, but that's way less than big galaxies like the Milky Way, which can have hundreds of billions. And a supermassive black hole is a type of black hole found in the centers of many large galaxies. These are the ones with masses from millions to billions of times the mass of the Sun, and they can strongly influence how their galaxies evolve. So here's what's interesting about SEG 1, which is a tiny dwarf galaxy. Evidence suggests that there may be a hidden central black hole there. The reason astronomers think that is because when they study the motion of the stars, their speeds and orbits, the stars move like there's something extremely massive sitting at the center. But the center doesn't show a normal bright object, so it's basically invisible in images, meaning it isn't giving off light the way stars do. The idea is, if you see strong gravitational effects but no visible source, a black hole becomes the best explanation, because only something incredibly dense and massive could control star motions like that. And the bigger reason this matters is what it tells us about galaxy growth. Dwarf galaxies like SEG 1 are kind of like labs for early galaxy formation. If small galaxies can host central black holes, that supports the idea that black holes in small systems could help seed the growth of larger galaxies over time. And that black hole galaxy connection is a huge part of the modern models of galaxy evolution. To wrap everything up, this is where telescopes fit into the big picture. Telescopes are essential in astronomy because they let us observe objects that are way beyond what the human eye could ever see, whether that's distant galaxies, star-forming regions, or planets around other stars. They also let astronomers track changes over time, like exploding stars, moving planets, and evolving galaxies. And one of the most powerful things telescopes do is break down light into information. By analyzing light, scientists can figure out what objects are made of, what conditions they're in, and how they're changing. So overall, telescopes are what connect our theories about the universe to actual evidence. They turn space from something we imagine into something we can measure, especially with instruments like JWST that let us see deeper and earlier than ever before. These are all of our work cited.
Wasn't that really interesting? I enjoyed learning so much about telescopes.
Thank you guys for watching,
This was our final for astronomy.
and I hope you learned more about telescopes.